I'm going to present material from a course I give, a beginning course on stability, elementary concepts about stability, emphasizing the Lyapunov concept of stability. Professor Luongo alluded to Lyapunov stability and how one has to be careful in interpreting it and applying the concept. And so what I will be doing implicitly is to restrict attention to the ideal perfect cases, primarily conservative systems with maybe some dissipation. And the motivation is to try to understand concepts like minimum energy. We've all heard about the minimum energy criterion or the energy criterion of stability. This really applies to conservative systems with possibly damping. But it's not clear why this criterion, which is a purely static test for stability, why it should have anything to do with what we really mean by stability, which is an inherently dynamical concept, as we've seen in the previous lecture. And it's the connection between the two goes back to Lagrange and Dirichlet, and later extended by Lyapunov. So what we'll do is reverse the order a little bit, discuss the Lyapunov concept of stability, Lyapunov functions, and then return to mechanics, finite dimensional systems, and extract the minimum energy criterion of stability as a special case of the Lyapunov theory. Okay? And then at more of a research level, we'll say in the 1970s and 80s, and 60s through the 80s, the extensions of Lyapunov's concept to continuous systems, continuum mechanics, structural mechanics, nonlinear elasticity, this was quite an active field. And there are certain technical challenges for continuous systems in extending the energy criterion of stability to continuous systems. It's not easy and requires a little bit of functional analysis. And I'd like to discuss that as well. So the survey problems for which rigorous interpretation can be given to the energy test for stability. So we'll be looking primarily at the so-called conservative systems. These are the ideal systems that Professor Luongo discussed before. And he cautioned us, rightly so, that these are quite limited in scope. However, there's still enough richness in this subject to attract our attention and our interest. And in particular, in nonlinear elasticity, this is the main arena for looking at stability. In other words, what is the connection between energy and stability? So, for example, in nonlinear elasticity, since the work of John Ball in the mid-70s, there's been a great deal of interest in establishing the existence of energy minimizers. Why do we care about energy minimizers? Because these are the stable equilibria in the Lyapunov scheme. So although this is a very limited scope, it's still a very rich field, rich enough, I hope, to justify a few lectures. Okay, so this will be my focus. And I have to apologize because I'm extracting this course literally from my handwritten notes that I used to base my course on. And these are intended for my assistance when I'm giving lectures, so the students never actually see these notes, and so they're full of writing in the margins and arrows and changes and so on, and so I have to apologize for the sort of cluttered appearance of the notes. But and also I will be skipping some material that is in here because it's not so relevant for a course like this. Yeah, you'll tell me how to send everything to the participants, and I'll do that. Yeah. Okay. Okay, good. So the basic idea, very elementary, the notion of stability, we can say that if a configuration of a system remains bounded for suitably bounded initial conditions, then we can say that the solution we're interested in, say we have a solution with some initial condition, we'll look at the finite dimensional case first and start even with a one-dimensional problem described by a first-order differential equation, the simplest possibility that relates to mechanics. If you have a solution starting from an initial condition, and you give a small perturbation of the initial condition, and if the solution to the perturb problem remains close to the original problem at subsequent times, let's say for all time, then we have the idea that the original solution is stable. Professor Luongo mentioned a more exacting definition of stability, which is essentially asymptotic stability, in which the perturbation of the initial condition, as time evolves, the difference in the solutions disappears to zero at a sufficiently long time. So that's a more exacting definition of stability. Let's start with a simpler one, which is just stability. So essentially, Lyapunov stability says it's like continuity. There's a continuous map of the initial conditions into the state at time t. So if you have two initial conditions that are close, then the state at time t, the two states at time t will be also correspondingly close. So this notion of Lyapunov stability is really almost identical, effectively, to the idea that the system maps the initial data into the solution in a continuous manner. Right? Small changes in initial conditions yield small changes in the solution. So this is the concept of stability, which is based on continuity. Essentially, the Lyapunov definition. So suppose you want two solutions to some initial value problem to be close, say epsilon close in the absolute value sense. If there's a number for this epsilon, for any epsilon, if there's a number delta such that the initial conditions being close in the sense of delta implies the state at time t, the states at time t being close in the sense of epsilon, then we can say that we say that the system is Lyapunov stable, roughly speaking. Okay. And there are many variations on the technical definitions of stability in the literature. I'll focus on the simplest ones, which are sufficient for us. Okay? Let's see. Okay, so it's just like this. So you have, say at some particular time, you have the states are close together within some epsilon bound, and the initial conditions, if they're close in a manner that depends on epsilon, so epsilon is a part of your definition of stability. What do you mean by stability? Two solutions are close. Well, how close? Epsilon you define as part of the definition of stability you introduce. And so the initial conditions must depend, this bound on the initial conditions is going to be controlled somehow by that epsilon. Okay? So that's essentially the continuous map of the initial conditions into the state at time t. So some trivial examples. Here's a first-order system. Suppose the right-hand side is 0, then of course all solutions are constants and equal to their initial conditions, so all solutions are stable in the Lyapunov sense. The right-hand side, let's see, say is x squared. Then you have dx dt as x squared. You can immediately spot a solution, say x equals 0. Say initial condition 0 at time t0. That's a solution for all time then. Look at any other solution will have this form depending on the initial condition y naught at time t naught. And you can make y naught, which is the same as the difference between the initial data, as small as you please. However, the solution ceases to exist at some particular finite time. So even though the initial condition is controlled, there is no control on the state at time t. There is a time at which the solution blows up, so we don't have stability in that case, obviously. Okay, so we can talk about a definition of instability, which is simply the absence of stability. So it means that a control on the initial conditions, if that yields that at some time, at some finite time, there is no control on the difference in the solutions, then we can say that the system is Lyapunov unstable. Okay. And asymptotic stability is then an obvious extension of the idea of stability. You have asymptotic stability if you have a stable solution, if the system is stable, and if the perturbation in the system decays to zero at large time, so that the system comes back to the original trajectory x of t at a large time. Okay, so here's a simple example. Dx dt is f, which is minus tx, some linear problem. Very easy to solve for any initial conditions, x naught or y naught, two solutions. So the difference in these two is initially bounded by delta and then decays to zero for large time. So every solution to this system is asymptotically stable. Okay. Professor Longo talked about equilibria in connection with what he was doing. So let's look at equilibria for a moment. These have the property that the solution, the initial condition is a solution for all time, essentially. And so that initial condition must satisfy the differential equation. And so the function on the right-hand side that defines the differential equation has to be such that when we put in this equilibrium point, we have identically zero. And that suggests that instead of trying to track individual solutions, we should ride along with a particular solution whose stability we're interested in. And so that from our point of view, as we move along with that solution appears to be an equilibrium solution to us. And then we can look at perturbations of that solution essentially as a perturbation of equilibrium. So suppose we have a solution coming from some initial condition at time t0. It satisfies our differential equation. We have another solution to the same system satisfying a different differential equation, different initial condition, same equation. And we can define the perturbation, which is the difference of these two solutions, emanating from some initial condition at time t0. So u will be the disturbance then of x. And we can write an equation for the disturbance. A differential equation for the disturbance is just the time derivative of the disturbance is the difference of the time derivatives of y and x. And we can write y as the perturbation plus the solution whose stability we're interested in. And this defines a new function. If x of t is known, it becomes a function of u and t with the property that capital F at u equals 0, zero perturbation, is identically 0. So the solution x of t corresponds to the solution u equals 0, and we can convert the original problem to the study of an equilibrium problem, u equals 0 identically for all time, starting from initial condition 0 at time t0. And that corresponds to the solution of the original problem, so that in principle at least, we can convert the study of the stability of a particular solution x of t to the study of the stability of an equilibrium point of an equivalent system. So that's convenient because then we have essentially one theorem that can cover all these possibilities. Okay, so this is just a restatement of the notion of Lyapunov stability in terms of the perturbation u. Let's see. Okay. So say we're doing a finite dimensional idealization of a structural analysis problem. Then our solution is a vector, say an n-dimensional vector consisting of the degrees of freedom. We have n degrees of freedom, x1 through xn as functions of time. And we can arrange these in a vector. And we can then, we're then interested in the study of an initial value problem like this. Even in mechanics, we can arrange our problem like this. We can extract an equivalent first-order system of this form with some initial condition, and this is then the finite dimensional version of what we've just been discussing. So the equation is described by an array of n functions which depend on the n degrees of freedom, and possibly also on the time as well. So, of course, there are many examples. In mechanics, a single degree of freedom problem, oscillating mass with damping, and elasticity, or spring stiffness, we can convert this, of course, to a first-order system if we wish by introducing x1 is x and x2 is the velocity of x, and so on. So that's, of course, very elementary. And then we have an equivalent first-order system where we extract a first-order system from the previous one. A pair of coupled mass spring damping systems, or a pair of particles that interact with each other via elasticity and damping. Of course, we can write that also as a first-order system. And so it's convenient. We can study essentially first-order systems. Okay. The general case, if you have, for example, a time-dependent, explicit time-dependent forcing function, you'll have an explicit time dependence in the differential equation. That's the hard case. That's the characteristic of a non-conservative problem, for example. For most of what we do here, we'll talk about autonomous systems for which there is no explicit time dependence in the differential equation. Okay. And so there's standard existence and uniqueness proof for the solutions of systems like this. Essentially, under mild conditions, we can establish the existence of a unique, smooth solution emanating from some initial condition. Okay. So when we talk about stability, extending the notion of stability from one dimension to finite dimensions, we need the idea of a distance or a metric between two states, x1 and x2, let's say. We'll call this metric, we call it rho. And it should have the property that when two states are not the same, the distance between them should be positive. And the distance between two states should be 0 only when the two states are the same. Okay? So this is a property that we would want to attach to the notion of the difference between two states. We would also like some additional properties. For example, the distance between me and you is the same as the distance between you and me, the symmetry condition. And it's convenient also to have a triangle inequality. The difference between these two states is bounded above by the sum of the distances between these pairs, and so on. So this is, for example, a property of norms. So a norm is a natural way of defining a metric or a distance function. Norms have some additional properties. Positive definiteness, we actually introduced that a moment ago for metric. So a norm can never be negative, of course, and can only be 0 when the argument is 0. So that's positive definiteness. And any scaling times the vector and the norm is scaled appropriately by the absolute value of that scaling, and the triangle inequality as well. So a convenient choice, and essentially one that we can use without loss of generality for finite dimensional systems at least, is a metric which is simply the distance norm, the distance between two states as described by the norm. Right? This gives us then immediately the triangle inequality from the property of norms. And also it has the nice feature that this metric then is a continuous function of x. In other words, if two states x and y are close in the norm, then the difference in their sizes is also close, are also close together. That's an easy consequence of the triangle inequality. Okay. So some simple examples of norms. Usual distance norm, Euclidean norm, it gives you the usual distance for the metric. Okay. The sum of the absolute values is another norm, in which case the metric is the sum of the absolute values of the differences in the components of the vectors. Or another norm is the maximum over the index set of the absolute value of the components, and so on. Absolute value by itself is not a norm because it can vanish for any one component, even if the vector, of course, is not 0. So that is not an actual norm. And the real distinction, one of the main distinctions between stability for finite dimensional systems and continuous systems has to do with the idea of norm equivalence, which you have in finite dimensional spaces. In finite dimensions, every norm is equivalent to every other norm. So that when you're discussing the stability of a problem, and therefore you're discussing the size of the difference of two states, the norm of the difference, it really doesn't matter which norm you use in your definition of stability. So if you study finite dimensional stability, there's never any particular commitment to one norm or another, and the reason is we have the property in finite dimensions of norm equivalence. We do not have this for continuous systems, and that's one of the things that makes the stability theory hard for continuous systems. The specification of the norm, or the metric, is an integral part of the definition of stability for a continuous system. So this is one of the technical difficulties or challenges in studying stability in continuous systems. So norm equivalence simply means if you have two norms, then you can find constants such that these inequalities are true. Say a norm, the first norm, a norm, say 1 is bounded above by a constant times norm 2, and likewise norm 2 bounded above by a constant times norm 1, and then therefore the same for the metrics. Okay? And so there are standard proofs of that norm equivalence. So that means you don't really have to commit to a particular choice of norm in your definition of stability. Not true for infinite dimensional systems. Here's an example, and here's also an example of my that motivates my apology for showing notes that are really only intended for the instructor to see and not for the student. So look at functions, say, they don't even have to be continuous. Forget about this. So look, here's one norm, essentially the L2 norm of a function f of x between 0 and 1. F of x is, say, 1 over the square root of x. This is unbounded then, whereas this absolute value norm, integral to the absolute value, is bounded. So we cannot have norm equivalence for these norms for functions. This is an example of an infinite dimensional space. And here's simply an illustration of norm equivalence in 2 dimensions. The circle represents the usual distance norm, and the box here is this norm. The sum of the absolute values generates this. If this is a constant, that curve corresponds to this box. And one can find constants such that this norm is bounded above by the usual distance norm, and vice versa. The distance norm is bounded above by the box norm. So that's simply an illustration of that idea. So this is all routine, sort of routine ideas. Again, one of the greatly simplifying features in stability of finite dimensional systems is, again, norm equivalence. Okay, so we can having these measures or norms now, we can trivially extend the definition of Lyapunov stability to finite dimensional systems in the obvious way. We simply replace the absolute values that we had in the one-dimensional case with the norms, or the metrics. Okay? In exactly the same definition. And I've said it many times, but the definition is independent of the norm because of norm equivalence in finite dimensions. There's an interesting connection between stability and uniqueness. A simple proof due to Mavchan, who was a major contributor to the conceptual foundation of stability about 1960 in the Russian journal. Suppose you have a solution starting from some initial condition x naught at time t naught, and suppose it's stable. Then you can show that it's unique as well. So stability is sufficient for uniqueness. Therefore, if you have a situation in which you have non-uniqueness, you don't have stability in the strict sense of Lyapunov, at least. So suppose, just In other words, suppose you have another solution which emanates from the same initial condition that this solution does, satisfying the same equation, of course. Then this stability of this solution implies that y is in fact equal to x for all t. And that's trivial to prove. It relies on this strict inequality in the definition of Lyapunov stability. So select epsilon, positive, and the idea then is that if there's a delta such that an epsilon bound on the state at time t is achieved whenever the initial conditions are bounded by delta, then x is stable by definition. Not asymptotically, but it fulfills our definition of stability. So let's proceed by contradiction. Suppose there's a time such that the two states are not the same, the two solutions are not the same at time t1. In other words, you have non-uniqueness. Then, of course, the distance between them is strictly positive because the norm is positive definite, and this argument is non-zero. So in particular, we can select epsilon to be that distance at time t1, strictly positive. The initial conditions are the same, so the bound on the initial conditions is always achieved for any finite delta. If we have stability of x, then the difference in the states has to be bounded above strictly by epsilon for all times greater than t naught. But by construction, this is violated at time t1. So the supposition, the assumption is false. Okay? There is no t1 such that y is not equal to x. So therefore we have uniqueness. So this is a kind of idea that, or leads us to the idea that a test for instability is the non-uniqueness of the solution to the initial value problem. And we'll return to that in the context of mechanics. Okay, so the great contribution of Lyapunov to the subject is the idea of a Lyapunov function, which allows us to assert that a system is stable without having to solve the complicated, generally nonlinear and difficult differential equation. So this connects later to the idea of the energy criterion of stability, which is essentially a static test for stability. We can assess the stability of a configuration without actually having to solve the equations for the perturbation. And this is the essence of Lyapunov's concept. Okay. So as before, we'll convert the study of the stability of our solution we just convert it to the study of the stability of the zero solution to the associated equilibrium problem, just by the same conversion that we had before. And many problems in mechanics, at least the ones that don't involve explicit time dependence on a forcing function, can be associated with an autonomous system without explicit time dependence. And we'll suppose we have an equilibrium state, which is then a solution for all time. In other words, if f at x naught is 0, then x naught satisfies the equation for all time, and we're interested in its stability. Okay, so we have here, we can convert that to the study of the zero solution of the equilibrium problem. So the idea of Lyapunov actually came after investigations in mechanics by Lagrange and Dirichlet, and Lyapunov extended their concepts to general systems described by systems of ordinary differential equations. So let's imagine we have a function v of x, a scalar valued function of the state, with these properties. So v of x is positive definite, never negative, and can only be 0 when x equals 0. X equals 0 is our equilibrium point. And suppose its derivatives are continuous, okay, then we can show that the function itself is also continuous. So it's an array or vector of partial derivatives, then we'll suppose to be continuous functions of the configuration x. How can you test this idea of positive definiteness and so on? Suppose, for example, that we pick some v of x that's twice differentiable, twice continuously differentiable, as a further special case. Just to illustrate an example. So then we can Taylor expand this function v of several variables, finite number of variables. This is the Taylor expansion for n variables. V at 0 is 0 by definition, and it has a minimum at 0 because it's positive definite, and if it's smooth then its derivatives are 0 at that state. And so the leading term is this quadratic term, and then there's a remainder, small o norm x squared, where small o means this, terms that go to 0 faster than the argument as the argument goes to 0. Let's see. So in such a case, v of x is approximated for small x, for small norm x, for points x close to the equilibrium point in this way. So we have a matrix of second derivatives, which of course is symmetric because v is twice differentiable. It's evaluated at the equilibrium state, so it's just a collection of numbers. And then we can write v of x locally in this form. Okay? So if v of x is positive definite, then for x not 0, we have this inequality, always. And if we pass to the limit, norm x goes to 0, then this matrix of second partial derivatives at the equilibrium point must be positive definite as a necessary condition. So we're in finite dimensions here. We have a symmetric n by n matrix, which will have then n real eigenvalues, all of them positive, because C is positive definite, and associated eigenvectors, which can be orthonormalized, right? And we can then decompose the matrix C in a so-called spectral form in terms of its orthonormal eigenvectors and the associated eigenvalues. And the eigenvalues, of course, are all bounded below by the minimum eigenvalue, which is positive. And then we have this inequality involving the eigenvectors, a matrix n by n that you can form from the columns of the eigenvectors. For any, this eigenvectors span, they span this n-dimensional space, so we can always resolve any vector as a linear combination of those eigenvectors. And then if we multiply through by xi, xj, and sum, we find that the right-hand side is just the squared distance norm, the usual distance norm, and so we have this inequality, where lambda minimum is strictly positive. Okay, so this means that our function v of x, call this a Lyapunov function. This is just an illustration for the special case in which it's twice continuously differentiable, is bounded above by a pure quadratic term with a positive coefficient, and some remainder, which is small o x squared, which means that it disappears. It's faster than x squared as x tends to 0. Okay? So we have this. If we divide by, consider states not 0, we have this inequality. And then this continued inequality, because of course r is bounded below by the negative of its absolute value. And in fact, we can use Taylor's theorem with remainder to estimate this r of x. And I'm not showing it here, but we can show that it's a continuous function of x, actually. And its limit as x tends to 0 then is 0. So it's continuous at 0. And what that means is we can make x small enough, say in some ball of radius rho, small enough, such that r of x over squared norm of x can be made as small as we please, let's say bounded above by 1/2 the minimum eigenvalue, or any number times the minimum eigenvalue. Okay, so for such x then in this ball centered at the equilibrium state, we have this inequality. V of x over norm x squared is then bounded below by 1/2 of the minimum eigenvalue, or any number here is okay. So then we have v of x positive definite, right? So in a ball sufficiently close to the origin, we can guarantee that this twice differentiable function is bounded below by the squared norm of x. So that's an example of then the construction of a positive definite function which happens to be twice differentiable. And the picture looks like this. Here's the actual v of x, and it's bounded below by this quadratic approximation in the neighborhood of the origin. Okay, so that's just a simple illustration of the notion of a positive definite function. So here's Lyapunov's idea. Here's our positive definite function. Let's say we're in 2 dimensions so that we can see what we're doing. We plot v of x above the plane, x1, x2 plane. And let's focus attention on a set of points where the norm of x is epsilon. So we're on the frontier, or the boundary of a ball, let's say, of radius epsilon in our configuration space here, x1, x2. And this set of points on the plane, the circle on the plane, if we use the distance norm, this is just the circle on the plane, will have a trace on the surface v of x that looks like this somehow. We have v of x is differentiable, continuously differentiable, so it's continuous, and this map of the map v of x will take this circle and map it continuously to some curve on that surface. So the basic Lyapunov theorem is this. Suppose we are looking at the zero solution to our equilibrium problem, or the equilibrium solution, which we can convert to the zero solution of our autonomous system. We can say then that the solution is stable if, so this is a sufficient condition, there exists a positive definite differentiable, hence continuous function v of x, whose time derivative on any trajectory of the system is never positive. And we then compute the time derivative for our autonomous system in this manner. Just using the chain rule, dv dx dx dt, here's the differential equation requires that is equal to f, the right-hand side of the equation. Okay. So, let's prove this sufficient condition by contradiction. So let's prescribe our epsilon and look at that frontier that we mentioned a moment ago, the set of points on the boundary of a ball of radius epsilon. Okay, I don't need that material. Okay, so this set, this frontier, is bounded, of course, from its definition. It's bounded in size. And it's also closed. It's the frontier of a ball, so it's a closed set. And so this frontier is a bounded and closed set in finite dimensions. And there's a simple theorem that guarantees then that this set is compact. In finite dimensions, all closed and bounded sets are compact, and vice versa. That simply means if you have a sequence of points in that set, and that sequence converges, then the limit is also in that set. We can look at the restriction of the function v of x to that set. Call it v star. That is now continuous on that set, because v is a continuous function everywhere in this ball. And therefore on this compact set, which is the frontier of that ball. And there's a simple theorem that every such function takes on both its maximum and minimum values on that set. And that's trivial to see in one dimension. I think everybody knows it. Continuous function on a compact set, the interval from 0 to 1, assumes both maximum and minimum values somewhere on that compact set. Okay? We don't have this property for infinite dimensional systems. For finite dimensions, this is an essential ingredient in the proof of Lyapunov's theorem. So our Lyapunov function v assumes both its minimum and maximum on this frontier of this ball that we've discussed. And so let's pick out the minimum. There's some minimum value, call it k, this minimum is strictly positive now, because on this set, this frontier of this ball, x is not 0, we're away from the origin, and norm x is then strictly positive, and we've also already indicated that v of x should be positive definite, so the minimum value on that set is a strictly positive number. For continuous systems, we don't have this essential simplification. All we can say is that all we can talk about then is the infimum of v for continuous systems, and the infimum may not be attained on this set. So that's a delicate issue in infinite dimensional spaces, which makes the subject of stability for continuous systems, if we try to look at it rigorously, it makes the rigorous theory much more difficult than it is for finite dimensional systems. So we have a strictly positive minimum of v of x on this set of points on the boundary of this, on the frontier of this epsilon ball. Okay. Okay, here's a bunch of stuff I don't need. Okay, so we know our function v of x is continuous because we've arranged it that way, and it vanishes at the equilibrium point. So we can always find a delta to make v at say x naught less than k. K is the minimum on the frontier, provided we make x naught less than delta. Okay? That's just because of the continuity of v of x. So this property that the time derivative is non-positive on any solution means that at any time t, v is bounded above strictly by this number k. Okay? So now we can set up the assumption that leads to a contradiction. Suppose x, the trajectory emanating from x naught is not stable. That means that there's a time t1 such that we're on the boundary of this epsilon ball. Where the solution pierces the frontier of that ball, so the norm at time t1 is epsilon. But, so here is the trace of the v of x for norm x equal epsilon looks like this. K is the minimum value, that gives a level, v of x equal k. But if this is true then the function is bounded below by k, and that's a contradiction because we just proved that v at any time is strictly less than k. So there can be no such time, and therefore x of t is stable. And that's essentially the simplest version of Lyapunov's theorem. Geometrically, what it means is, if you compute the time derivative, the velocity always opposes the gradient of the function. So if you're on any level of the function v of x, the gradient is this way. The velocity always makes an inner product that's non-positive. So the trajectories can never escape this ball, this region. And then we have stability. So some trivial illustrations for the simplest mechanical system we can think of. So let's look at a nonlinear oscillator, a mass sliding without friction back and forth under the influence of a spring, and that's all. So here's the equation of motion. And suppose x equals 0 is an equilibrium position, which means f at 0 has to have the value 0. We'll suppose that if we compress the spring, we require if we extend the spring, we need a positive force, and if we compress it, we need a negative force. Okay? So this force extension relationship for the spring can look like this, let's say. We can make our first order system out of it if we wish. And x equals 0, which means 0 position and 0 velocity, both, is the unique equilibrium point of this system. And so now the problem is to find an appropriate Lyapunov function. Did it stop working? Okay. in the general application of Lyapunov's method, this is a kind of an art form to find Lyapunov functions, and at one time there was a small industry in the literature of generating Lyapunov functions, which are just functions that meet these conditions of Lyapunov's theorem, which is merely a sufficient condition for stability. In mechanics, a potential choice, which suggests itself from the principle of conservation of energy in an ideal system, is the total mechanical energy, kinetic plus potential. And for this problem, the kinetic energy is just this quadratic term in the velocities. And the potential energy is the integral of the force-stretch relation of the spring. Potential energy we can show is positive definite under the assumptions that we've made on the function f of x. For an extension, the p of x then is, from the graph I've just shown, is clearly positive for x strictly positive. Also for x strictly negative, it's again positive, and it's 0 if and only if we're at the equilibrium point. So we have this p of x, this that I'm constructing here, is a positive definite function of x. That by itself is not the Lyapunov function, however. We can show that the total energy, kinetic energy of y, that's a positive definite function of y, plus another positive definite function of x, that's a positive definite function of the array xy. Okay? So we're really in R2. This one-dimensional problem, mechanical problem, is a two-dimensional problem in terms of our notation. So if we call kinetic plus potential, we call that the total system energy. That's a strictly positive definite function of the state, x vector consisting of x position and velocity. And we can show that it's continuously differentiable, and hence therefore continuous, which we can see immediately anyway. Its time derivative on any trajectory of the system is 0, right? And that's enough to guarantee that the conditions of Lyapunov's theorem are met. So we have a positive definite total system energy, and hence our equilibrium state is stable in the sense of Lyapunov. And we can make that conclusion without having to solve the difficult nonlinear system associated with this nonlinear spring. And that's the essential utility of the Lyapunov concept. Here's something else I don't need. Something about asymptotic stability, but I'll come back to it next time. Get to something useful here. Okay. This is something about some technical stuff about asymptotic stability, which is a bit harder to prove, and so I don't want to discuss it. Let's see if I can find something useful. No. Okay, so excuse me a moment while I find the appropriate. Okay, here we are. Okay, so we have the Lyapunov theorem, which supplies us with sufficient conditions for stability in the dynamical sense that a trajectory that starts close to your equilibrium state will remain close for all time. Equally important from the point of view of mechanics, or maybe even more important, are tests for instability. Right? If we fail to satisfy the hypotheses of the Lyapunov stability theorem, we know nothing at all, because this is simply a collection of sufficient conditions for stability. If we fail to satisfy these hypotheses, we have no information. So we like conditions that ensure instability as well, and that's less well studied. There are a number of criteria for instability that have been proposed. The most useful one from the point of view of mechanics is due to Gtf's instability theorem. And it's somewhat similar to Lyapunov's theorem in the sense that we construct a function with certain properties that guarantee instability of the equilibrium, and then we can make a conclusion about instability without having to solve the equation of the system that describes the dynamics of the system. So let's suppose we have a function u of x, and it's such that there exists a region in say a ball of size epsilon in which the function is strictly positive. So there exists a subdomain of points in which this function is strictly positive. We'll call that subdomain U+. So graphically, here's an example here. A region U+ where the function is positive. And suppose we have a set U star where U is equal to 0. And we'll suppose that that set U star includes the origin, which is our equilibrium. So here's a line U star on which this function assumes everywhere the value is 0. And on this side, it's strictly positive. And U bar plus will be U plus, the closure of this will be U plus U star. Okay? And we'll consider, in a stability problem, in reality, we cannot control the initial condition. Think of the initial condition as a perturbation caused by the outside world. And we have to admit all possibilities for perturbations, because we have no real control over them. So let's look at a perturbation, or an initial condition, that is somewhere in this region U+. What we'd like to show is that under these conditions, the trajectory is forced to escape this epsilon ball at some finite time. And so these conditions guarantee instability of the equilibrium. Okay, so let's look also now at a punctured disk, let's say, C delta, in which x is bounded strictly away from 0 and less than some finite size delta, smaller than epsilon. Okay? And we're interested in the stability of the origin, the equilibrium solution. Okay. And we'll pick our initial condition to be in the intersection of this C delta with U+. So sufficiently close to the origin, and then we'll show that the trajectory must escape that neighborhood. So we'll suppose that we have such a U of x, which is continuously differentiable, and that the right-hand side of our differential equation is continuous in this region as well, so that when we compute its time derivative on any trajectory, the chain rule delivers this formula. And let's suppose, as one of the conditions for this function, that this time derivative is positive whenever x is in this region U+. Then, these conditions, I have not formulated it precisely here, but these are all the conditions we're going to, is strictly this U star is not contained in that region, so M is strictly positive. And its derivative is continuous also for such x. So this derivative as a function of x achieves its minimum value, which is also strictly positive. So we can integrate the inequality, and we find with M strictly positive that there is a time, t1 let's say, such that U exceeds its maximum value, which is a contradiction. So the assumption that the trajectory remains in this ball is violated. Let's see. The assumption that x does not remain in the ball, in other words, that we have instability, leads to a contradiction. Let me see if I'm saying that. Okay. The assumption that x remains in the ball leads to a contradiction. That means it must escape the origin, and then the origin is unstable. So that's actually a much simpler theorem than it seems to be, the way I've presented it. And here we have some very simple examples of a system, say n equal 2, here's a nonlinear system, and we'll always look at the origin, the stability of the origin. We can try a function v of x squared plus y squared, on any trajectory of the system. Its time derivative is non-positive, in fact strictly negative. In fact, then we have stability, and we can even show asymptotic stability in this case. Here's another system of two equations. We're going to look at the stability of the zero solution of these two. Here's an example of the so-called Gtf function. There's a region in the xy plane where this is positive. There's a curve u star where this is 0. And in the region where U is positive, we can make its time derivative positive as well. And so the Gtf theorem guarantees that the origin is unstable. And so on. A few other simple examples. Here's another system, nonlinear system. This turns out to be a Gtf function, at least when x is sufficiently close to the origin, so that we can neglect these terms here as higher order terms. That means if we take epsilon small enough in our definition of stability, then that definition will be violated at some finite time by virtue of Gtf's theorem. Okay. Simple system of equations. I have here Aij of t, but I promised to do only autonomous systems, so let's say that this is just a constant matrix. Suppose it's a skew symmetric matrix, and let's look at a function v of x, a candidate Lyapunov function, which is just the distance norm of x. Look at its time derivative on any trajectory. The skew symmetry of A says that that's 0, which satisfies the conditions of Lyapunov's theorem. So the zero solution of this system is stable by Lyapunov's theorem. Something more relevant for people who study equilibria is the notion of gradient flow. Maybe you've heard of gradient flow. You'd like to solve the equation fx equals 0, an equilibrium point. F is a complicated function and it's difficult to solve, so we embed the problem into a dynamical problem, let's say. Solve x dot equal df dx, with df dx equals 0 at the origin. Let's try a Lyapunov function equal to minus f. V dot then can always be shown to be non-positive. And if f is negative definite, then v will be positive definite and x equals 0 is stable. So actually the equilibrium problem then would correspond to these equations here. And the idea is this can be quite difficult to solve in practice. So instead we embed this into a dynamical problem. And in the case of f negative definite, we have a so-called gradient flow algorithm for computing the equilibria. But we don't even have to do that. We can guarantee, if we're interested only in the stability question, we can guarantee that the origin is stable for a negative definite f, and so on. Here's maybe a more explicit example of the Gtf theorem, the system. Two equations, nonlinear system. The origin is always a solution. This function x squared minus y to the fourth is a Gtf function. It's positive here, and its time derivative is positive in this region U plus, let's say. So if we have initial condition in this region, and we can't prevent that in practice, we have to allow that possibility, then that initial condition will escape any epsilon ball at sufficiently large time, so we have instability. Okay, so simple examples. Let's see. We can extend ideas to non-autonomous systems, but I won't do that here. Let's see what I want to do next. Okay. Wait a minute. So let's talk a little bit about mechanics. And the appropriate setting for a finite dimensional discussion of mechanics is, of course, Lagrange's equations. So I'll give you a very quick survey of Lagrange's equations. The right way to derive them is by looking at the principle of least action and extracting Lagrange's equations as literally the Euler-Lagrange equations of the least action or stationary action principle. Let's proceed from a more elementary discussion, which may be more familiar to students of engineering at least. Suppose we have n particles and they're constrained in some way. So the position vectors of these particles have to satisfy some constraints. So for example, you have a mass on the end of a rigid pendulum, then the distance of that mass from the origin is fixed in time. So that's a constraint on the position of this type. And we'll suppose that all the constraints in the system are solvable so that we can express the position vectors of each point in the system, each particle, in terms of so-called generalized coordinates. And if there are n generalized coordinates sufficient to describe every state of the system, then we have an n-dimensional or finite-dimensional system of dimension n. Okay? And we'll assume these position functions then are differentiable, in fact twice differentiable functions of these generalized coordinates. Okay, so if we have a system of particles then, say capital N particles, we have the kinetic energy of the system, the usual a half mass times velocity squared. And these velocities, the derivatives of the position vectors of each of the particles, can be evaluated by the chain rule in this way in terms of the generalized velocities, the time derivatives of the generalized coordinates. Okay. And the kinetic energy then can be expressed in this way in terms of a positive definite quadratic form in these generalized velocities. Because the original kinetic energy is positive definite by assumption, or by construction, because the masses we assume are strictly positive. That will mean this quadratic form is strictly positive, so this so-called mass matrix, mu, will be a symmetric positive definite matrix, n by n matrix. Okay? And so this would be a positive definite quadratic form in the velocities. But of course, when writing this in terms of generalized coordinates, it can be some nonlinear function of the positions, the generalized coordinates themselves. Okay. So it's positive definite, its determinant then is positive, and it's invertible. Mu is invertible. Okay. A very nice translation of a book by Gantmacher, Lectures in Analytical Mechanics, Mir Publishers, is an excellent source for finite dimensional dynamics. So we have the force on the particle alpha, the alphth particle, and of course the equation of motion for that particle. We can use it to generate an expression for the power, and that's just of course the time rate of change then of the kinetic energy of that particle. And then sum up all the contributions from all the particles, and we have the time rate of change of the total system kinetic energy, like so. And we can write that power, instead of using the velocities of the position vectors, we can write it in terms of the velocity, the generalized velocities, just by using the chain rule. And in so doing, we introduce the so-called generalized forces, like so. Okay? So inserting the equation of motion for the particle number alpha, we then have this expression for the generalized forces, which are power conjugate to the generalized momenta, the time derivatives of the coordinates. Actually, I'll reserve the name momenta for something else, which is the derivative of the kinetic energy with respect to the velocities, small p. So from one of this expression for the kinetic energy, we have this. And we use the chain rule to connect the actual velocities to the generalized velocities. And then we can compute this derivative from this. This derivative turns out to be the derivative of r dot with respect to q dot is just, interestingly, the derivative of r with respect to q from this equation here, where q and q dot are independent variables in these partial derivatives. Okay, so we can write the momenta in this way then. And we can replace dr dot dq dot by dr dq. And the generalized forces then can be written this way. And we write that as the time derivative of the whole thing minus, of course, the term, we just use the product rule here. So this is dr dq dot, and that derivative is computed this way using the chain rule. And we can write that as the derivative of r dot with respect to q. we simplify this thing as derivative of r dot with respect to q, so that this term on the far right just turns out to be the derivative of kinetic energy with respect to the configurations. Okay? So this equation at the top then, it reduces to this, and this is the so-called Lagrange equation, derived from the equation of motion for the system of particles. With apologies to Francesco, I should do this via a variational method to begin with. But this is elementary derivation. So this is our system of equations for mechanics. Okay? There's an easy generalization of this, relatively easy. It's very to rigid bodies. You don't find in the literature explicit derivations of Lagrange equations by this method from the equations of motion directly for rigid bodies, interestingly enough. But in this excellent book by C.C. Wang, who's a major contributor to continuum mechanics, you will find such a derivation for rigid bodies, and also in a paper by a colleague of mine at Berkeley. A repetition of the same procedure starting from the equations of dynamics for rigid bodies. Okay, so let's go back to our kinetic energy, which is this positive definite quadratic form in the velocities. The momenta, the derivatives of the kinetic energy with respect to the velocities, can then just be, in the sense of partial derivatives, so we hold q fixed, can be represented this way. And of course mu is symmetric, so we have this form. In other words, the generalized momenta is just the product of the mass matrix with the generalized velocities. And mu is invertible, so we can interchange the momenta with the velocities in every discussion about the dynamics of the system, if we wish. I want to talk about conservative forces because this connects to the notion of minimum energy as a test for stability. Conservative forces are those for which, let's see, well, let's consider an example. If you calculate the work done in moving from time 0 to time 1, let's say, the work is just the integral of the power. The power is this is the generalized forces. And suppose Q, the generalized forces only depend on the configuration. So there's no dependence on velocities, no damping, and no explicit time dependence as you would have if you have an explicit time-dependent forcing function. Let's just consider this special case here. Then the work done is just then a path integral in Q space. Right? Q dot dt is dq, and the capital Q's only depend on Q, so this is a path integral in the configuration space, like so. Okay, a path going from Q0 to Q1, where these are the values of the state at times t0 and t1. Suppose now that we have a situation in which the generalized force is the gradient of some function in this Q space, configuration space. So suppose there exists a scalar valued function of the state such that capital Q is the derivative minus the derivative of E. Then this inner product, this linear form, is just an exact differential. And so the work done is just the difference in the values of this, we call this energy, E, at the two states, time 0 and 1. Okay? And the integral then, the work done, is independent of the path that followed from Q0 to Q1. It only depends on the end states, the configurations themselves. And we'll see in a moment why this now is called a conservative force. And conversely, if the work done is identically 0 in any closed path in Q space, then you can show that the generalized forces must be of this form, from Stokes' theorem. The gradients it must be expressible as a gradient in this way. Okay? In this case, for forces of this kind, the generalized forces here on the right-hand side are like this. And so this suggests that we introduce a new function, we'll call it the Lagrangian, the kinetic energy minus this E. This E we'll call potential energy of the generalized forces. So the Q derivative of this Lagrangian, or of this difference, is the derivative of the Lagrangian with a minus, and the derivative of kinetic energy with respect to velocities is just the derivative of L with respect to the velocities, and so on. And so we can recast the Lagrange equations in this special case in this form. It's a very simple form. Okay, so this suggests that it would be useful to consider general forces of this type. So we can always imagine that any generalized force we could decompose into a part which is a gradient and a part left over, which could depend on other aspects of the problem, the state, the velocities, and perhaps an explicit time dependence. So Professor Luongo before mentioned the idea of a follower force, for example. This would be included in this term here. Or an explicit time-dependent applied forcing function would be included here. So we can then rewrite Lagrange's equations in this way in terms of these additional Q prime forces. When those additional forces are zero, we can generate an integral of the equations, which is just the so-called Hamiltonian, or the total mechanical energy. When we obtain that easily, let's look at a time derivative of this Lagrangian using the chain rule. Insert Lagrange's equations into that time derivative. Then that brings the generalized forces, or these additional forces now. And we recognize this as the time derivative of this combination, Q dot times dl dq dot. And if we define now H to be this combination minus the Lagrangian, we can compute this expression for its time derivative. So if these additional forces of the sort that would involve an explicit time dependence, or for perhaps damping and so on, if these are not present, then this Hamiltonian, so-called, is conserved in time. That's the conservation of mechanical energy. Okay, so we can show that. dl dq dot, those are the generalized momenta, which are related in this way to the velocities via the mass matrix. And the dl dq dot q dot then is just this. That's twice the kinetic energy, so the Hamiltonian is twice the kinetic energy minus the Lagrangian, which is kinetic minus potential. So that's potential plus kinetic. That's the total mechanical energy. So the conservation, or the equation for the Hamiltonian reduces just to this. The rate of change of the total system energy is balanced by the power of these additional forces. These additional forces are zero if the forces are gradients of an energy E. In that case, the total system energy is conserved. And so in that case, we talk about conservative forces. So conservative forces are the ones that lead to a first integral of the equations of motion. The total energy, system energy, is constant in time. Okay, so forces of this type generate this property, and we therefore call them conservative forces. Just a couple of notes based on the basic Lagrange equations. We can cast them in this form in terms of accelerations and our mass matrix here. And because this is invertible, we can now solve explicitly for the accelerations in this form. And then we can cast this as a conventional first-order system by introducing the notation for the velocities, and then the equation of motion is of this type. So that suggests for an n-dimensional system, we define a 2n-dimensional vector consisting of the positions and the moment and the velocities. Okay, so then we can cast this as a first-order system, x dot equals fxt, and so on. If we prefer, we can, in place of the velocities, we can use the momenta, because there's a one-to-one relationship between them, and introduce a different 2n-dimensional vector consisting of the positions and the momenta, and we have an alternative then first-order system. So in dynamics, often people use the so-called canonical form of the equations, which is based on this Hamiltonian that we've introduced. These derivatives here are just the generalized momenta, And we can replace the velocities by a function of the configuration and the momenta. Okay? And so we can write the Hamiltonian as a function of position and momenta, like so. And that allows us to put the equations in so-called Hamiltonian form. For example, the derivative Hamiltonian with respect to momenta we can compute from the equations, and we find that the velocities then, the Fj, that's the right-hand side of the equation of motion, to give the velocities, those are just the gradients of the Hamiltonian with respect to the momenta, and so on. Okay. Actually, that's just a definition. We didn't use the equation of motion yet. Here are Lagrange's equations. The LdQ involves the HdQ, which we can compute ultimately, and we find this equation. So we have Q dot is dHdP, and P dot is minus dHdQ, plus these additional non-conservative forces. And so as before, we can immediately obtain our conservation law. dHdt is the power of these additional forces, these non-conservative forces, so if there are none, then we have a conservation of the Hamiltonian, etc. Okay, so this brings us to essentially a version of Lyapunov's theorem for finite-dimensional mechanical systems. This theorem is due to Lagrangian Dirichlet, and it actually predates Lyapunov. Lyapunov extended the theorem, their theorem, to general systems of differential equations. And we'll look at the case of conservative loading only, which, as we know from our previous presentation, is the idealized case. The idealized case is already technically a big challenge in the infinite dimensional case of continuous systems. So I want to focus attention on this for now to see what the structure is that we might be able to use later for continuous systems. So let's make a 2n dimensional vector from the configuration and the velocities. Okay? Or we can use the momenta in place of the velocities without affecting the argument. So let's introduce a 2n vector which consists only of the configurations, and another 2n vector which is the velocities. And then our state of the system is essentially the direct sum of these two, or is the sum of these two, right? So our first order system then would be in terms of x. And so our distance norm, the usual distance norm, is then, because the x space is the direct sum of these two, the squared distance norm is just the sum of the squares of the individual distance norms, like so. So let's use this norm, which is the distance norm in our 2n dimensional space. Or we could have any other norm that we please by virtue of norm equivalence. So we'll put Lagrange's equations in this first order form using this vector x. And our equilibrium configuration, let's say, is associated with the state q sub e for equilibrium and zero velocity. We can, of course, always redefine q of t this way, replace it by q minus q equilibrium, so that we can focus attention on the zero solution, q equals 0 and q dot equals 0. Okay, then x equals 0 is the solution we're looking at. Okay, and we investigate its stability. So suppose in some neighborhood of the origin in q space alone, configuration space, we have some ball here, norm q bounded above by some constant. Suppose we have this function E, this potential energy, suppose we have it being continuously differentiable and positive definite, okay, vanishing only when q is 0. Then, by itself, this guarantees Lyapunov stability of the equilibrium. So, minimum energy then, the potential energy being positive definite in a neighborhood of equilibrium, is enough to guarantee Lyapunov stability in the dynamical sense of the equilibrium. Okay. Of course, such an E generates vanishing generalized forces at equilibrium, right? Because if E is smooth and has a minimum at 0, then of course its derivatives are 0, and so these generalized forces are 0. But that doesn't mean the system, the actual physical forces in the system, are all 0. We can have so-called reaction forces associated with the constraints. They're simply orthogonal to these tangents, to the configuration trajectories in terms of the generalized coordinates. So if you have a ball on a rigid pendulum, you can have a force perpendicular to the trajectory of the ball and still have 0 values of the generalized forces. Okay? Okay, so the theorem is about the state which consists of q and q dot, which is the vector x, two-dimensional vector. So let's introduce a ball in the q dot space. We had a ball in q space. Let's extend it to q and q dot space in this way, the same radius k. And in particular, the norm of q itself is bounded above by k, so that we're in this ball bk, where we have this smooth potential energy function that's positive definite by assumption. Let's, guided by our earlier example of a one-dimensional oscillator, let's imagine, let's try for Lyapunov function the Hamiltonian of the system, the total system energy, which is just the kinetic plus potential energies. So the kinetic energy is always positive definite. So in this ball, we have V positive definite. In other words, V can never be negative because both of these are positive in this ball. And the question then when can V be 0? That's true if and only if the kinetic plus potential energies are 0. This is the sum now of a positive definite quadratic form in the velocities and another positive definite function of q, the configuration. So the sum can be 0 if and only if the individual terms in the sum are separately 0, which means both q and q dot are 0. So we're at the origin 0. So V can vanish only at the origin. Therefore, V of x is positive definite in this ball. V is continuous because kinetic and potential energies are continuous. Potential energy by assumption is continuous because it's differentiable. And its time derivative on any trajectory is equal to 0. So we have stability of the origin by virtue of Lyapunov's theorem, because of Lyapunov's theorem. Okay? And here are the details, which are simply a repetition of the basic Lyapunov theorem that we had before. Okay. Let's see. As a practical matter, to implement this criterion, it's not so easy to implement in general. To check that we have a potential energy function and to assure that it's smooth, hence continuous, and positive definite is not a trivial task in general for a high-order finite-dimensional system. And so let's examine something called the second variation criterion. And this is intimately connected to bifurcation, buckling. So we want to connect, ultimately, buckling analysis to the notion of stability. So suppose E is twice differentiable in some neighborhood of the origin in Q space. So in particular, then, its second derivative is continuous, and the function and its first derivatives will then automatically be continuous. So we can look at a ray through the origin to any point Q, defined in this way, alpha Q for alpha between 0 and 1. And we can apply now, in this ball, the so-called Taylor theorem with remainder, which I alluded to before at the beginning, and obtain an estimate of this potential energy, EQ. So we Taylor expand it, and Taylor's theorem with remainder says, well, this version of it, we can truncate the expansion here at second order, provided we evaluate the matrix of second derivatives of E at some point intermediate between 0 and Q along this ray, described by alpha Q. So this is an exact expression for a twice differentiable function, Taylor's theorem with remainder. And the first term here is q times the derivative of q, the E with respect to q, at 0. But we're supposing 0 is an equilibrium configuration, so the generalized forces acting on it are 0 at that configuration. So we can, the energy then looks like this at some alpha q. This form is not so convenient, so what we'll do is take this term, this is the potential energy, and we'll add and subtract the same thing, where S is the matrix of derivatives at the equilibrium point. That's called the stiffness matrix of the system at the equilibrium point. So the energy then looks like a quadratic form with constant coefficients, a symmetric matrix, and this remainder then looks like this. The second derivatives evaluated at some alpha q minus the same second derivatives evaluated at 0. That now will be a function of q, a nonlinear function of q. Call it r of q. What's interesting about it is that it is under our hypotheses, it's a continuous function of q, which vanishes when q equals 0, right? As q tends to 0. And that's an essential ingredient. So for q non-zero, we can define small r in this way, so that we can write the energy in this way. Factor out the squared norm of q. We have this stiffness matrix where u is now the normalized or unit vector associated with the configuration, and then we have this small r of q. Okay, we know from Lyapunov's theorem, or the Lagrange theorem, that a positive definite potential energy is a sufficient condition for stability. So let's examine the consequences of that assumption that the potential energy is positive definite. So then we have this for q non-zero, where u is the normalized configuration, and r looks like this. Okay? So here, the q dependence is here. These are unit vectors. The q dependence is in here, and because E is twice differentiable, as q tends to 0 in norm, this will approach this, and then we have r of q goes to 0. Okay? So if we divide, we have this inequality here and allow norm q to go to 0, we find this inequality is a necessary condition for positive definiteness of E. Just the stiffness matrix at equilibrium is positive definite, at least with respect to unit vectors. We can then multiply this inequality through by squared norm of q to get positive definiteness for all non-zero q, right? Positivity for all non-zero q. So the stiffness is positive definite as a necessary condition. What about the converse? Suppose the stiffness is positive definite at the equilibrium position. Then we can show that in fact the potential energy is a positive definite function for q sufficiently close to the origin. How do we show that? Well, let's look at this quadratic form in terms of unit vectors, normalized configuration. This Sij is just a matrix of numbers having nothing to do with u. So this is trivially a continuous function on this unit sphere in n dimensions. That unit sphere is closed and bounded, hence compact in finite dimensions. So this continuous function will assume its minimum value somewhere on that unit sphere. Right? We'll call that, we'll call that minimum value 2 times lambda. And our hypotheses now guarantee that lambda is strictly positive, that minimum is strictly positive. So we can say for any vector on the unit sphere, this quadratic form is bounded below by this strictly positive number lambda. So if we multiply through by the squared distance norm of q, we get this inequality. So our expansion for the energy then guarantees that our energy divided by square norm of q is bounded below by this number lambda plus this remainder term we had before. So this is a finite, this is an exact, there's no series expansion here, this is the complete representation. And of course R is bounded below by the negative of its absolute value. However, R is continuous and 0 at the origin. That means we can make R as small as we please by making Q sufficiently close to the origin. So we can make R at Q, which is this difference because R at 0 is equal to 0. We can make that difference as small as we please, say 1/2 lambda, if we choose Q sufficiently close to the origin. In other words, for Q inside this ball that we mentioned. So then this inequality becomes this, and we guarantee then that the energy itself, which is a nonlinear, in general a non-quadratic function, is bounded below that by this positive quadratic form. So therefore it's a positive definite function. Okay? So the second variation, with the stiffness matrix being positive, guarantees at least a local minimum of the actual the actual finite potential energy. Okay? Not merely its quadratic approximation, but the actual function itself. Okay. So a positive definite stiffness matrix gives us conditional stability of the equilibrium because it guarantees this inequality which meets the hypotheses of the Lyapunov theorem. So that's very useful because the test is only on the stiffness matrix at the equilibrium point, which is just a matrix of numbers whose definiteness can be investigated easily algebraically. In fact, we can show that this 2 lambda that we introduced here is the smallest eigenvalue of this stiffness matrix. Because from the construction we've made, 2 lambda, there exists a unit vector on this unit sphere and dimensions such that this quadratic form is equal to this 2 lambda. That's how we constructed it. So we can associate the configuration with that particular unit vector simply by multiplying through by the squared norm of an appropriate configuration. And this means that for any other Q, we have an inequality here because Q naught, there's a minimizing value of Q which yields alpha. So for any other Q, we have this. So that suggests we define a function J of Q, let's say, which is the difference, the left-hand side minus the right-hand side, which we can write this way. So this function J of Q is never negative, and it vanishes at Q0, right? Because of this property here. So J of Q has a minimum at Q0. So let's derive a necessary condition for that. Let's perturb Q0 in this way. Pick an arbitrary vector V and let T be a parameter. Not the time, but just any parameter. Say that encloses an open interval enclosing the origin, T equals 0. Then we can write J of Q as a quadratic function of T, the parameter. And it has to be non-negative. So we can associate J of Q with a function of T, phi of T, which looks like this. It's quadratic, which is minimized at T equals 0. So, and it's a smooth function of T, obviously, and so its derivative vanishes at T equals 0. And the derivative then extracts only this linear term at T equals 0, which we can write as this inner product with the arbitrary vector V, and F here is just this coefficient, this V. So this is an inner product that vanishes for all choices of V, so we can prove easily that then F must be 0 as a necessary condition and also sufficient. F equals 0 means Q0 is an eigenvector of the stiffness matrix with eigenvalue alpha. So alpha, which is 2 lambda, is an eigenvalue of the stiffness matrix. And we constructed it such that it's the lowest eigenvalue. Okay. We've already proved under these conditions that the conditions of Lyapunov's theorem are satisfied, so we have stability. But let's look at it in a bit more detail. We have E, if the stiffness matrix at equilibrium is positive definite, E is bounded below by this quadratic form for some strictly positive lambda, the smallest eigenvalue of the positive definite stiffness matrix. The kinetic energy is also a quadratic form in the velocities. Okay? And mu we know is positive definite. And the reasoning we had just a moment ago ensures us of the existence of a minimum eigenvalue mu, okay, for each fixed q. And that minimum eigenvalue is positive. And in fact, if we recall the comments of Professor Luongo, in this case, we have symmetry in mu. These eigenvalues will actually be continuous functions of q. So that means in our ball, say b rho, the neighborhood of the origin, the eigenvalues these are continuous so that they will achieve their minimum values in that set, compact set in finite dimensions. So that means twice this function b, the Hamiltonian essentially, is bounded below by a positive number times the squared norm of the velocity plus another positive number times the squared norm of the configuration. And so we pick the minimum of those two numbers, and then we have v bounded below by a positive number times the squared norm. So v satisfies this condition for some positive number c, hence it's positive definite. A slightly more explicit version of the Lyapunov theorem showing explicitly simply that we have a positive definite function b. Okay. This brings us to the notion of the critical load, so-called. And this is defined by the existence of some configuration such that this quadratic form vanishes at that configuration. So the possibility of this happening depends on the nature of the stiffness matrix at equilibrium. The stiffness matrix contains information about the equilibrium state that we're studying. So embedded in here are the forces at equilibrium as well. So this stiffness matrix incorporates information about the loading to the structure also. So this means the associated eigenvalue, the smallest eigenvalue, vanishes, which means this q bar is also then an eigenvector of the stiffness matrix. And this is the equation of linearized equilibrium, adjacent equilibrium. So this is the equilibrium equation linearized about, so this is, you have two equilibria, let's say. The original one at q equals 0. Then if this condition is satisfied, we can have another one in the neighborhood of the first one. And its state is described by this equilibrium equation. So for this to be possible, we have to have a zero determinant of this stiffness matrix. And this is the so-called adjacent equilibrium or critical load condition. This is the interesting condition, the interesting problem from the point of view of mechanics. To find conditions of loading that give you a zero determinant of the stiffness matrix at equilibrium. Okay? Because at that point, our second variation criterion breaks down. We no longer have a positive definite second variation, therefore we no longer have a positive definite energy. So we lose the hypotheses of the Lyapunov theorem, and we have no information at all about stability. So we have a potential problem here in the sense that when this happens, if there's a state such that the determinant of the stiffness matrix becomes singular at our equilibrium state that depends on the system and the loading associated with it, then our sufficient conditions for stability break down. We have no information. So this is a potential problem from the engineering point of view. In this case, we require further information. Here's some irrelevant material about that I won't need for now. Let's see. Oh, okay. Okay, so I have a few minutes, I think, right? So we were talking about estimating the potential energy in the neighborhood of an equilibrium, Q equals 0. And that suggests that,
Your SIG
is the matrix of second derivatives of the E, energy, at Q equals 0, which is the equilibrium. So it's just a collection of numbers, nothing to do with Q. Okay? Yeah. And so, yeah, the E describes the external forces, but they're conservative forces in this case. So we're looking at, later on I will extend the idea to include dissipative forces, say dissipation, damping. And then we'll talk briefly about non-conservative forces, where we really need Angelo's techniques to help to solve the problems, because in that case we have no Lyapunov Theorem available to us. Okay. So I mentioned that when the stiffness matrix ceases to be positive definite, the hypotheses of the Lyapunov Theorem or the Lagrange Theorem, the same thing essentially, fail. Then we have an open question. At this condition, is the system stable or not? In other words, if you have a bifurcation according to the linearized equations of equilibrium, is the original equilibrium stable or not? Potentially unstable because the hypotheses of the Lyapunov theorem are no longer satisfied. But they're simply a set of sufficient conditions for stability. So failing to satisfy them means we have no information at all. Okay? They're not necessary conditions. They're simply, we have no information, so we need to conduct a more detailed analysis. Okay? So this suggests now, so the second variation was simply then, in that case, the leading order estimate of the potential energy in the neighborhood of the equilibrium. So let's expand the description. Let's look at higher order variations. So we'll introduce these variations, so-called first order variation, second order, third order, so on. The first variation of the energy is just the vector of partial derivatives, I'll call it E sub I. And these vanish at 0 because 0 is an equilibrium state at which these generalized conservative forces are 0. Okay? You can have constraint forces acting on the system, but they're not involved in the power, so they're not affecting the generalized forces associated with this conservative system. So the first order variation is just this. The first derivative times the perturbation Q minus 0, perturbation from equilibrium. The second variation is just this quadratic form we had a moment ago. And we'll put the 2 factorial here. Eij is the matrix of second derivatives of the energy, and at equilibrium, I called it the stiffness matrix, Sij. So this Eij at 0 is just the stiffness matrix we introduced a moment ago. The third order variation we can introduce in the same way. Right? This is a homogeneous cubic function, and the coefficients are the third order derivatives evaluated at the equilibrium state. And then we can continue to the kth order variation, and we have this collection of all kth order derivatives at equilibrium. Okay? The interesting feature about these variations is they're homogeneous functions in the sense that the kth order variation is homogeneous in Q of degree k, which means this. If we replace Q by a scalar times Q, lambda, not the lambda from before, just any scalar, then the result is the same as lambda to the power k times the original kth order variation. That's an immediate consequence of the definition, right? So this is a very useful algebraic property that these kth order variations are homogeneous of degree k. Okay, so for Q non-zero, we can choose lambda to be the reciprocal norm of Q and conclude that the kth order variation evaluated on a unit vector, which is the normalized configuration, is this, like so. This turns out to be useful. So, recall what we just proved. If you have a positive definite stiffness matrix at the equilibrium point, this is a function of the configuration at equilibrium and the loads applied at that state. That means the second variation we've just introduced is positive definite. And we've shown that in a sufficiently small neighborhood of the origin, then, that implies that the actual finite potential energy itself is a positive definite function. And that's enough to guarantee the hypotheses of Lyapunov's theorem. And so we have stability of the equilibrium. So positivity of the second variation, positive definite stiffness matrix at equilibrium, guarantees a conditional stability. If we have a perturbation in some small neighborhood of the origin, then the trajectory will stay in that neighborhood of the equilibrium state. The question then arises, what if the second variation vanishes? This is incorrect here. What if the matrix vanishes? That's not relevant. The question is, what if the second variation vanishes, which is the quadratic form based on S? That's the critical load condition that we just mentioned. That's the condition of adjacent equilibrium according to the linearized theory. What if you have the possibility of a non-zero adjacent equilibrium? That means the second variation vanishes for such a configuration. What happens then? So let's generalize that second variation criterion. Suppose all the variations vanish up to order k-1. So this extends the idea, the first order variation vanishes at equilibrium because that's what equilibrium means, right? So we're interested in the generic situation in which, say, the first k-1 variations are 0, and the first variation which is not 0 is the kth order variation. So suppose the kth variation is non-zero for some q in a neighborhood of the origin, some non-zero q. Of course, when q is 0, the variations vanish from their definition. They're homogeneous functions. In this case, when all variations up to order k-1 are 0, then the potential energy is exactly equal to this. It's the kth order variation at equilibrium, and a remainder, which is the kth order variation on a ray from equilibrium to our point q. This is just Taylor's theorem with remainder. Okay? The point then being that this arc q goes to 0 as q goes to 0. Okay, because the variations are homogeneous of degree k, we have this algebraic property. So we can divide by the norm of q to the kth power, and we have the kth variation evaluated on the unit sphere in n dimensions, plus this remainder, and this remainder is guaranteed to go to 0 as q goes to 0. Okay? Because when you divide this by norm q to the k, you get unit vectors here, but this then is continuous in q, in particular continuous at the origin. So this remainder vanishes as you approach the origin. Suppose, let's repeat the discussion we had for the second variation. Look at the consequences of the energy itself being positive definite in a neighborhood of the origin. Then this representation shows that this combination here is positive definite. The first term is independent of the size of q, and the second term disappears as the size of q goes to 0. So a necessary condition for E of q to be positive, strictly, is that the kth order variation is strictly positive. Okay? And well, at least on the unit sphere, and then we can use the homogeneity of the kth variation to conclude that it's a positive definite function of q as a necessary condition. We'll show in a moment that this condition actually requires that k be an even number. You can never have an odd order variation which is positive definite, which it's easy to show. Let's look at the converse. Suppose the kth order variation is positive definite. So then it's positive on the unit sphere, but as a special case, because of course u is not 0 on the unit sphere. It's continuous by construction. It's a kth order monomial, right? So it's continuous. So because the unit sphere is compact, again in finite dimensions, there'll be a place on the unit sphere where the minimum value is achieved, call it lambda sub k on the unit sphere. So for any other point on the unit sphere, Ek will be no smaller than lambda k. And the homogeneity of the kth order variation then gives us this inequality. If we multiply through by norm q to the kth power, we get this. So the kth order variation is bounded below by q to the power k, norm q to the power k. So we have the same argument as before. Divide by norm q to the power k is bounded below by this number, strictly positive, plus this remainder, which is bounded below by minus its absolute value. This is now continuous at the origin because of Taylor's theorem with remainder. We constructed it that way. That means we can pick a small enough q to make this number as small as we like. Let's say we like this number. Then for small enough q, we can ensure that this inequality is satisfied. 1 minus 1 over k factorial, let's say. So then the total energy is bounded below by this strictly positive form on q, which means E is positive definite in a neighborhood of the origin, in some neighborhood of the origin. And that means we have stability, provided our initial conditions begins in this small neighborhood, we will stay in that neighborhood. In this sense, the equilibrium is conditionally stable because we're putting a bound on the size of the neighborhood in order to guarantee, in order to use this continuity argument. Okay? So the kth order, if all variations up to order k minus 1 are 0, and if the kth variation is strictly positive, then we have Lyapunov stability. Interestingly, this means the sufficient condition is only consistent with k being an even number, and that's easy to see. If you introduce s, which is just minus q, and use the homogeneity of the kth order variation, homogeneous of degree k, you get this. So when k is odd, you get minus 1 here. So Ek at s is minus the Ek at q. So if there's a non-zero q that makes EKQ positive, then there's a non-zero s that makes it negative. Right? In this case, we say that the kth variation is indefinite. There exist arguments that make it negative. Okay? So the only way to guarantee the positive definiteness of this kth order variation is to make k an even number so that this situation doesn't happen. Okay? So this notion of a kth order variation guaranteeing conditional stability in the sense of Lyapunov is only meaningful when k is an even number. So second variation, fourth variation, and so on. Just some properties we may use later, I think. Functions that are homogeneous of degree k. There's a nice theorem, Euler's theorem, that guarantees that this sum, x times df dx, or for us x will be q, is just k times the function. It's a simple proof which is called Euler's theorem for homogeneous functions. Okay. And I'm over time, so I better stop. And then next time we'll talk about instability. We'll develop a version of Gtf's theorem for mechanical systems. And then we'll talk about damping and do a number of examples. And then what I want to do is move to continuous systems, which are far more difficult from the point of view of actually establishing a Lyapunov type stability theorem, or also a Gtf type instability theorem. And then we'll make a catalog of problems where we can prove these results. These are relevant in structural mechanics, especially. And then we'll show why we cannot do these, we cannot produce these results for conventional finite elasticity. Okay? And then I'll discuss some extensions by Coiter, which allowed him to prove a result for finite elasticity as well. Okay, thank you.